We are in section 1.2 and we're continuing our study of the nature of problem solving. The crux of this section is going to be the order of operations, and you probably remember something about the order of operations from way back when you were in school, and it has to do with this acronym PEMDAS. You may have learned it as Please Excuse My Dear Aunt Sally. But let me go over that with you. It starts out with parentheses, and then it ends with addition and subtraction. It is in order from left to right, and that is very, very important. That is the most important part of this, is that everything is in order from left to right. So the P stands for parentheses, and it's important that you know that the parentheses can look very different. So you can have parentheses like you normally see it. You can have brackets. You can have these curly kind of brackets. You can also have absolute value, which is basically the distance from zero, which is always a positive distance. Some of my students used to call those the sticks. So just however you learned it, all of these are considered parentheses. Also, the numerator or the denominator of a fraction is considered a whole unit. We're going to see that in some of our examples today, and so you'll see where that's going to play in, but that's all parentheses. The second is exponent. Exponent is done by notation. You'll oftentimes see this this raised little asterisk here. A lot of times this is called, sometimes you'll see people call this a carrot top. This is 8 raised to the second power, or 8 squared. If you see a 3 here, people will call that 8 cubed. What that means is that is 8 times 8. So oftentimes this is used for the multiplication symbol. So 8 times 8, which is 64. So that's what this means, 8 with the little upper script 2. And so then you have 8 times 8. So that's what exponent means. Then you have multiplication and division. Now, these two go together, and what it means by they go together is that multiplication is in order from left to right, multiplication and division. So if you see the division and it becomes before the multiplication, then you would do the division first. So a lot of students get tripped up with this, and that's where order of operations usually gets people mixed up, is with the multiplication and division. So a lot of times when I get to this, I will say it really fast. Like I will just say multiplication, division. And so multiplication, you will see written with the little star. You will see it written as an X, a dot, 2 numbers written right next to each other, or letters. You'll see it written and separated by parentheses. A lot of different ways that multiplication can be represented. Division can also be represented with a slash. It can be represented in fraction form. It can be represented with the division symbol. So multiplication and division go together. And then similarly, addition and subtraction go together. Addition and subtraction is what you typically remember addition and subtraction being. Thank goodness. And so, but they are also in order from left to right. Okay, so let's apply this in an example. Looking at an example, this will be a simple example, 10 plus 4 times 3. I've given you the PEMDAS acronym in the corner for us to be able to use. So what we're going to do is we're going to use this, and we're going to start out, we're going to look, there are no parentheses, there are no exponents, so then I'm going to go straight to multiplication division. And I do see a multiplication here. So that's going to be the first thing that I'm going to do. And so I'm going to say 4 times 3. 4 times 3 is 12. Now what I'm going to do is I'm going to bring down the 10 and the plus. So I'm going to write those exactly like they were. Then I'm going to now have this next part of my problem, which is 10 plus 12, and that is 22. And so I didn't have any more multiplication or division, which meant that I could go on to addition and subtraction. So my final answer in this case is 22. So this was a more simple problem that did not involve too many steps, but we're going to look at some problems that involve more steps. So let's look at another problem. All right, now this particular problem, I always find it very interesting because I'm going to read this problem to you. 520 plus 480 divided by 20. 520 plus 480 divided by 20. 520 plus 480 divided by 20. Notice that when I read it to you, all three of these problems sound like they are exactly the same. In actuality, they are three separate problems and they look different. And so let's see if they are indeed different or if they are the same problems or not. So let's just take them one at a time. The first problem, we're going to just work them one at a time. Okay, so the first problem, we are going to do the order of operations. There are no parentheses. There are no exponents, multiplication, division. This slash is a division. So I'm going to work that division problem. 480 divided by 20 is 24. Then I'm going to bring down 520 plus 24, and I end up getting 544. So that's my final answer. Now, this second problem, we're going to go ahead and move quickly into this one. The second problem, again, no parentheses, no exponent. I do have this division problem, and it's written as a fraction. It turns out that these two problems are exactly the same. It is just two different ways to write the fraction 480 over 20. So this is 480 divided by 20 written in a fraction form with a horizontal bar or a slash bar. So really these are going to end up being worked out the exact same way. You're going to take 480 divided by 20, and that's going to be 24. And then you're going to add the 520 to it and get 544. So you should have expected to get the same answer. Now, this last problem, while it looks like it could be the same problem, is actually a very different problem. So 520 plus 480 over 20. Now, it turns out that everything in this numerator, fractions work very differently, and things that are in the numerator and things that are in the denominator, they like to stay together. So all of those things in the numerator, we are going to have to keep them together. So it's almost as if there is an understood set of parentheses. So we have to consider that all of that stuff has to work together. So we actually have to keep that together, and we're going to have to work that out first. So we're going to work that out first, and whenever we do that first, we actually get 1,000. So that 1,000 divided by 20, then that becomes 50. And I'm sorry, my head is in the way. But that is the answer. 1,000 divided by 20 is 50. Okay, so that is a huge difference from 544. So you can see the order of operations makes a huge difference whenever you're working these problems out. All right, let's look at another bigger example with order of operations. All right, in this example, we've got a lot going on. And so when you are looking at this particular example, you are going to see that we have got brackets, we've got parentheses, we've got division, we've got multiplication, we've got just a lot going on. So what you want to do is that you want to just really kind of assess all of the different things that you have going on. When I look at this, I kind of see that I kind of have some natural breaks going on here. I've got this 10 guy that's out here by himself. I've got this big group right here because this bracket joins here. And then I've got this bracket in here. So I kind of want to go ahead and divide this guy up into 3 big groups. And in my mind, that's how I'm going to divide this up. I'm going to think of him in 3 groups, and I'm going to try to kind of keep these 3 groups together. So that's how I'm going to work this problem out. So the first thing I'm going to do is I'm going to just drop that 10 down. Now the reason why I drop that 10 down is because inevitably if I don't drop him down, I will forget him. I do that all the time. So I go ahead and drop him down and I write him down. Now the next thing is that I go ahead and we're going to look at this second group. And in this second group, I'm going to look at the whole thing and I see a big set of parentheses. Now, once you go there, you have to start over again with PEMDAS. So you're going to start over again and you're going to say, okay, do I have any more parentheses? Well, yes, actually you do. You've got another set of parentheses in here. So you start over again. Do you have any more parentheses? No, I don't have any more parentheses. Good, you can go on now. Inside there, do you have exponents? No. Do you have multiplication division? Yes. Then do it. So I have 15 divided by 5. So I can do that division. 15 divided by 5 is 3. So then what I'm going to do is I'm going to say 3 times 7. Now, I said 3 times 7. That's where this came from. Where did this plus sign come from? That came from right here. So you have to keep all of these signs where they came from to begin with. You have to preserve all of the original signs. Okay. So now I have 3 times 7. And I'm going to go ahead and finish that off and say that that is 21. And then I brought this plus sign here. So this whole middle section reduced down and simplified to 21. Now I'm going to come to the third section and we're going to do it the exact same way. So we're going to do the whole thing. I'm going to start over again with my parentheses and I'm going to say 4 times 3. So then I'm going to get 12. And then I'm going to bring down that divided by 6. Okay. Now, 12 divided by 6 is 2. All right. Now, I'm getting simple. Each time it should get a little more simplified. So it's looking prettier. Thank goodness. So 10 plus 21 plus 2, order from left to right. 10 plus 21 is 31, and 31 plus 2 is 33. So that's my final answer. Okay, it's 33. All right. Now, if I go too fast in these videos, you just pause me. That's the great thing about a video is you can just pause and rewind and replay. So you're just like, man, she's talking too fast. Or I already know this, let's fast forward. So yeah, you can just do all of that. All right, let's move on. Okay, inductive reasoning. Problem solving first by observing patterns and then predicting answers for more complicated problems. So we're going to talk about different types of reasoning skills. Mathematics deals with a lot of reasoning and logic. And so inductive reasoning is looking for patterns. So we're looking for patterns. We're going to use those patterns to predict answers for more complicated problems. So I wanted to throw this in here because we do this a lot in church work. So the question, and this kind of question came up actually in our church. So when does a growing church know that it's time to consider building a new sanctuary or worship center? So you may have, if you've had to call your state office or your association office, and if you've ever been in a growth spurt or something like that, and you've had to rebuild or remodel. So there's a formula that they kind of use, and that formula that they have found is that when your current building reaches 80% capacity, then they have found that it's time for you to really consider building or looking at other options, whether that's going to be multiple services or whatever is going to be, but you've got to be thinking about it, because at that time, that's going to be when things are going to start getting uncomfortable. And so how did they come up with that? Well, they came up with that by observing patterns from, hundreds and thousands of other churches that went through similar growth patterns. So they used inductive reasoning and put those patterns together. So that's just kind of a ministry way of inductive reasoning. So now let's talk about in mathematics, how does this equate? So in your homework, you have this problem, and everybody always, I've gotten emails about this already this week. This homework problem says, this problem is modeled after example 1. Find the requested pattern. Enter the first 3 numbers of the pattern as a comma-separated list. And then it just says 5 pattern. And it makes absolutely no sense. And so you're just like, what in the world are they talking about? So it turns out that they are talking about example number 1 from your textbook. So you actually have to go into your online text from section 1.2. You actually have to find example number 1 from section 1.2. And then you have to read that problem, try to figure out what in the world they're saying, and then figure it out. So I'm going to help you with it. Don't worry. So it turns out this mathematician, really smart guy named Polya, came up with this. And Polya found out that I really wonder how these guys came up with all of this, but I'm glad they did, and they had much more time on their hands than I do, because I don't have time to figure all this out. But anyway, what he did is he sat around and he said, I find it very interesting that when you say 1 times 5 and you get 5, and then when you say 2 times 5, and then he said that's 10. And what he did is he added the number of digits in the answer. So he added, so the answer 5, there's only 1 digit, so there's nothing to add together. It's just 5. But then 10, what he did was he added 1 and 0, and he got 1. Okay. Then 3 times 5 is 15. And he added those digits together, and he got 1 plus 5. Which is 6. Then he said 4 times 5 is 20. And he added those digits together, and he got 2 plus 0, which is 2. And then he keeps going. Like he says 5 times 5 is 25, and 2 plus 5 is 7, and so on. Okay, the answer to this question, the answer that you would put into WebAssign, is 5, 1, 6. All right. Now, that still makes absolutely no sense, except that you get the correct answer. So you're welcome. That's how this works. If you have the 5 pattern, if you had the 8 pattern, you would have to say 1 times 8, 2 times 8, 3 times 8, and do the same thing with the 8 pattern or the 9 pattern or the 7 pattern or whatever. And so, but anyway, what he found was that no matter what, with all of the numbers, you eventually get, so all of these right here, so you eventually get all of the digits and they just repeat. Like you get all of the digits 0 through 9 and they end up repeating when you add them all up. And that's what he found. And it was just fascinating to him. And I'm glad it was fascinating to him. Yeah, not quite so fascinating to me, but I'm glad it was fascinating to him. I don't want to discredit Polya, but anyway, there you have it. The answer is 516, and you get credit for it. There you go. But only if you have the 5 pattern. I'm not saying you're going to have the 5 pattern because you may have something else. So just be careful with that. All right, next. The sum, what is the sum of the first 14 consecutive odd numbers? All right, so we need to talk about what does all of this mean first. So consecutive means in order. Odd means the odd numbers, which are 1, 3, 5, 7, 9. The sum means you're adding them all together. Okay, so let's talk about this. The first odd number is 1, obviously. Okay, if you wanted to add the first 2 odd numbers, you would say 1 plus 3, and you get 4. If you added the first 3, it would be 1 plus 3 plus 5. You add them together, you get 9. 1 plus 3 plus 5 plus 7, that's the first 4 numbers, you get 16. The first 5 consecutive odd numbers, you add them together and you get 25. Now, 14 numbers is not a whole lot. So really, you could go through and do this, but that really, I mean, it's cumbersome. And what if they asked for, I mean, and you may, because everybody has different problems, so it may ask you for the first 50 consecutive odd numbers. Now, I really don't want to sit here and add up all 50 consecutive odd numbers. You may want to, but I don't want to. So if there's a pattern, I would really love to know it. So if you look at these answers, 1, 4, 9, 16, 25. You may not recognize those numbers right off the bat, or you might, but in math, those are special numbers. Those are actually called perfect squares. So it turns out that that first number is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and so on. So it turns out that this question is really just a matter of asking whatever number they're asking you for. All you have to do to get the answer is just square it, and you get the answer. So it turns out that you just take the number and square it. So in this case, you would say 14 squared, and the answer is 196. Now that's a whole lot better than sitting here writing them all out, especially like what if it asked you for what is the sum of the first 5,674 consecutive odd numbers. Yeah, I don't think you definitely don't want to add all of those up, right? And so all you'd have to do is plug that into a calculator and write that monstrosity of a number down. And so then it's much easier if you can come up with a pattern. So this is where inductive reasoning becomes very helpful. Okay, you're welcome. I know you love me. Okay, now the second type of reasoning is deductive reasoning. This is problem solving based on formal structure of logic. Now, we're going to go over some different deductive reasoning problems that the book uses. I did want to share a story that I thought you would appreciate. I used some deductive reasoning this summer in one of my seminary classes. So I had a Bible class. I shall not tell you which class or which professor, but it was a Bible class. And keep in mind, I'm a counseling student. So, a Bible class, and I had to memorize all of these facts. It was just facts, 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 facts. And so I just worked my hardest to memorize all of these facts that they asked for. And so it was about this particular, it was about this particular person, this particular preacher. And buddy, I thought I knew everything about this preacher. I knew his wife. I knew his first church. I knew, I think I knew his birthday. I don't know. I knew where he was from. I knew all of these different things. I was just like, I had flashcards. I was just like, man, I know everything about that dude. And I was just so proud of myself. And so I was just all ready to take that test. And so I was like, I'm just so ready for it. So ready for it. And bless me if the test doesn't come. And the question was something like, what is the title of his first book? Or maybe his second book. It was some fact I didn't know. But I knew 50,000 other facts about the guy, right? And so I was just like, are you kidding me? I have spent days and hours and hours and hours studying and knowing this guy in and out and in and out and in and out. And the one question you ask me, I don't know. So I used my deductive reasoning. I was just like, oh, this will be okay though. You know what I'll do? Because it was one of those essay type questions or something. You could type your answer in. And so here's what I thought. I thought, I'll be real smart here. So I said, so here I am typing, right? And I'm typing and I'm just like, I don't know that answer. But I do know, and I typed like everything. I typed the maximum number of characters that I could fill in that space. And I typed everything else that I knew about the dude. Like everything else that I knew about the guy. And I thought, surely that would impress the professor or professor's grader. It didn't. I got it wrong. So, the moral of the story, deductive reasoning does not always get you where you want to go. However, I tried. Anyway, I did try to use my deductive reasoning skills. That's why I'm a mathematician type person, not a Bible scholar. And I'm not bitter about it either, as you can tell. Anyway, let's go on. Okay, in our mathematics, we are going to use these Euler circles to check the validity of the argument. All right, so let's talk about these circles. So you're going to come up with, I'm going to show you how to use these particular types of circles by definition to check, and this is the type of deductive reasoning. And so you're going to have these are called syllogisms, are these like 3-line little syllogisms, and they want you to use these circles to be able to check to say, is this a valid statement or not? So the first statement, the first line is what tells you which set of circles to use. There's 3 different sets of circles that you can pick from. So the first line says all dictionaries are books. Okay, that key word there says all dictionaries are books. Now, that is where we're going to start. And so I'm just going to get, we're going to work this example, and then I'm going to show you all 3 of the different kinds, okay? Because it'll make a little more sense. So the first one is that all P are Q. So all P are Q. This is all of one thing fits into another category. All of one category fits into another category. And that's how I knew that this worked for this situation, because it's saying all P dictionaries fit into a second category, Q, which is the books. So I'm going to let dictionaries be my P and books be my Q. Okay, let that sink in, because that's your first step, is trying to figure out what is P, what is Q, which set of these little circles to use. Okay, so once you figure that out, the second thing is to go to your second line. This is a dictionary. All right, now we need to test the validity of this particular statement. So to test the validity, we've got to kind of put a test mark somewhere in this particular picture. So if this is a dictionary, I'm going to put a star where this dictionary would be. If this is a dictionary, where is it going to land in this picture? So if it landed out here, would it be a dictionary? No. If it landed right here, would it be a dictionary? No, because it would be a book, but not necessarily a dictionary. It would have to land in this green part in order to be a dictionary. So I'm going to put a star in that green circle because it says this is a dictionary. So if I'm going to test the validity of it, I'm going to test it out where it says this is at. Okay, now to test it, I want to test, is this a true statement? Therefore, this is a book. So is this, since this is little star is right here, does that star mean that it's a book? Is this star in the circle that makes it a book? Well, yes, actually it is, because it's in this bigger circle that says it's also a book. Okay, so it turns out that this is a valid statement. So, yes, this is a valid statement. So we're okay with this. So then you would just check that this is valid. You checked it. Okay, now you have, I said earlier that there were 3 different situations. So let me show you those 3. So the first one is the all P are Q. So all of one thing fit inside of another category. Okay. Now then you have kind of the opposite of that. That no P are Q. So in other words, these 2 things are totally separate. So the 2 objects would be totally separate. Nothing. They're not alike at all. Okay. Then you have a third set, which some P are Q. Okay. Some P are Q. And so they kind of have this little overlapping part where some of them are and some of them aren't. So now you have to kind of decide which one fits where. Okay. So we're going to do another example that is not quite cut and dry, and we're going to see which one it works out to be. Okay, use Euler circles to check the validity of the argument. If you like potato chips, then you will like crinkles. Okay, now notice there was all, none, like all, no, or some. Now I look at this and I see if you like, then you like. I don't see all, I don't see no, and I don't see some. So I'm not seeing those keywords. So I'm a little confused and I'm just like, I wonder which one this is. I'm not quite sure. So now I need to kind of think about it because it's going to fit into one of the three. So I need to try to figure out which of the three it fits into. So if you like potato chips, then you also like crinkles. If you like potato chips, then you will like crinkles. So actually it's talking about everyone who likes potato chips also likes crinkles. That means everyone who fits into potato chips fits inside of crinkles. So it turns out that all potato chips are crinkle lovers. You can reword it. All potato chip lovers are crinkle lovers. Couldn't we reword it that way? Yeah, we could. So, all potato chip lovers are crinkle lovers. If you like potato chips, you're going to like crinkles. So, we're going to put potato chips here for P, and we're going to put crinkles here. Okay, so it turns out to be that same example, but it was kind of disguised. Now, here's the next thing though. This is a little different. This says, you do not like potato chips. Okay, well, if you don't like potato chips, let's think about where you would live in this diagram. If you don't like potato chips, well, gosh, you could live way out here outside of the diagram altogether, right? You live way out here. So let's think about that. If you live way out here and you don't like potato chips, let's see if this is valid. Therefore, you do not like crinkles. Do you not like crinkles? That's right, you don't like crinkles. So I would say that's valid. However, there's somewhere else you could live. You could live right here. There's somewhere else you could live. You could live here and also not like potato chips, right? There's two places you could live. You could live right there. If you lived right here, you still don't like potato chips. But if you lived right here, do you like crinkles? You do like crinkles if you live right here. So it turns out that this is not a valid statement. Isn't that tricky? That's tricky. I know, right? So that's how you check these things. They're just a little tricky. Okay? So all of those are tricky. That's how you check them. Okay, we're going to look at, I think, one more. Yes, homework 12. All right, homework number 12. Ask about these squares. How many squares are there in the figure below? And then it's going to give you a number for n, okay? When it gives you the number for n, that means how many columns and rows are in the diagram, okay? So let's kind of let's kind of work through this and figure out what they're talking about. All right, so the first thing we're going to look at is when n is equal to 1. When n is equal to 1, you just have this one little square. So how many squares are in it if n is equal to 1? Only one square. Okay, easy peasy. Now, n equals to 2. If n equals to 2, then you have this right here. This is what you have, this square 2 by 2. Okay, if you have a 2 by 2, then you're going to have 1, 2, 3, 4 little bitty 1 squares. Okay, so you're going to have 4 of those. Then you're going to have 1 big square, which is a 2 by 2 square. Right? So it turns out you're going to have 5 squares total. Okay, everybody good? All right, now what if you have n equals to 3? If n equals to 3, you're going to have this little diagram thing here. N equals to 3, you're going to have how many of those little ones? How many of those little ones? You're going to have like 9 of them, right? You're going to have 9 of them. So that's 9. Then you're going to have how many of these 2 by 2s? So we're going to have 1 here. We could have another 2 by 2 here, another 2 by 2 in this little corner, and another 2 by 2 in this corner. Hopefully you can see that. So that's 4. Yeah. Okay, so that's 4 of those. Then we are going to have 1 big one, which is that 3 by 3. Are you seeing a pattern here? So each time we are adding the same thing from the previous. So notice we're adding 4 plus 1, which was 4 plus 1 from the previous. And we just added 9. Now 9 came from 3 squared. 3 squared is 9. 2 squared is 4, right? So all that I do is I just say 9 plus the previous number, which was 5, and I got 14. So at n equals to 4, how many 1s am I going to have? I should have 4 squared, which is 16. Then I'm going to have all of this over again, right, underneath it. So I'm going to have 9, 4, 1, and I add all of that up. I get 30. So what are you going to have like if n equals to 5? So I'm not going to work it out for you, but I wanted to set this problem up to help you understand how to work this out. So you should be able to work this out now, because I know that several of you were having a hard time with this problem. If you need to have some more attempts, just send me a message and let me know, and I'll be glad to give you an extra attempt so that you can go back and try this problem. Like if you ran out of tries, I'll give you an extra couple of attempts so that you can go in. So just let me know. But I want you to try that. So if n equals to 5, then you would take and do 5 squared and add that to 30, and you should be able to get your answer right. And then so on. Okay? All right, hopefully that helps you out on number 12, and that should finish off 1.2. All right, if you have any questions, let me know. Let your professor know. Thanks so much, and good luck with section 1.2.